H of a group G. So, and we might underline that, indicating that that would be the key thing to define, or that might be in italics. A good answer to this kind of question would be a subgroup H of G is normal if and only if for all G in G, GH, G inverse is equal to H. Something like that. That would be all. You wouldn't have to say a group is an object, is a set, together with a multiplication. A subgroup is a subset, such that blah, 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 blah. Okay, it would just be, just define the term that's sort of specified. And we'll have about 10 such definitions. The second section will be a true-false. We will make some statement. And you'll get +1 if you get the true-false part right, and you'll get +4 for the description of why it's true or false. So it's not enough to just answer false. You have to indicate why it's false. So you might say the statement, here's an example of a question. 1, the group GL2R is abelian. Okay? That's a good statement. So the answer would be false. And you'd say because we can find two matrices, A and B, with AB not equal to BA. That would be about half credit. That would be about +2. And to get the full thing right, you'd want to give a specific counterexample, e.g., A is equal to 0, 1, 1, 0, and B, I hope this works, is equal to 2, 3, 0, 0. And I think if you multiply those in two opposite directions, you get two different answers. And then you might calculate AB and BA and show that they were not equal. Yeah?
Will counterexample always be sufficient?
Absolutely. In proving something is false, you just have to give one counterexample. That's the beautiful thing about mathematics, right? So, and the more specific the counterexample, the happier I am. That's why this statement at least shows what you mean by the group being non-abelian. That would be something, and this would be much better. Okay? And if it's true, you should give the argument why. So I'm trying to think of a quick and easy well, you should, you know, you could, and again, it wouldn't require, so a group G of order 21 contains a subgroup of order 7. I don't know. 7 to 1, 1, 7. A normal subgroup of order 7. And then you'd say true, and the proof would be there exists a subgroup H of order 7 by the CELO theorem. Number of such divides 3, which is 21 divided by 7, the index, and is congruent to 1 mod 7. And the only numbers that divide 3 and are congruent to 1 mod 7 would mean there's only one of them. Hence, H is unique and normal. So that would be enough of a justification for a statement like that. I just want people to understand on this exam, it's always important to know when have I done enough answer. So we're not going to have huge amounts of space between the true-false or between the definitions because you're not supposed to prove the CELO theorem to do this or anything like that. Just quote what you need. Okay, and then the third part of the exam is how many true-false? There are about 25 true-false questions. Is that? Pardon? That's about where it stands. They're not that difficult, believe me. I mean, both the definitions are really, just the fundamental things. We're not going to ask you to define anything esoteric. And the true-false statements, you should be able to at least decide whether it's true-false very quickly, and then the reason shouldn't be more than a sentence or two. So I would imagine, that this part of the exam might take 20 or 30 minutes, and this part of the exam might take an hour. That sort of thing. And then the final part of the exam will be 4 to 5 problems. Of a slightly more involved nature, where we'll say, prove that we might say, here's an example of such a problem. All right, well, I prove that any finite integral domain is a field. That would be a kind of statement. And then you'd have to say what it meant to be an integral domain and what it meant to be finite and why elements had inverses. And I won't write out the proof, but this is the kind of level of statement that would be at the end of the exam. And again, we're not throwing any curveballs here. Almost anything you've seen on this exam has been either carefully done out in class or done as a problem, etc. We're not going to tell you about a new mathematical structure that you now have to investigate based on the knowledge you have of rings and groups and fields. Okay? So that's what I have in mind for the exam. And I'm going to do a review today, or at least start the review, and then Peter's going to finish it on Friday. And of course, next week when you actually start studying, because the exam is next Friday, Peter and all of our wonderful Liz will be available to, and not to mention JC. Is JC around? They'll all be available to help you if questions come up. But as I say, just make sure, I've tried to emphasize how much this course is really a basic language course. Make sure you understand the basic concepts of ideal, etc. Now, I should also say, one second, I'll get to you. One second. I should also say that probably more of the exam than of the course will be on the latter part that we covered, the material on commutative rings and ideal theory. That's the part we haven't tested yet. And so we've had tests on groups and on vector spaces and groups of motions of the plane and things of that nature. There'll be some questions on that. But I would say that probably only a third of the course might have been about commutative ring theory, but probably about half the exam. You think that's fair, Peter? So, because that's the new material we'd be testing here. Okay, now, good.
Would you ask us to define the theorem, like say what the theorem says in the definition part, or?
No, and you mean, it's just terminology. So I wouldn't say, state Gauss's lemma for primitive polynomials or something like that. But I might say, what's the content of a polynomial or something like that. So you don't have to identify the full, or I wouldn't say in the definition, what is the Silo theorem? Okay? But there will definitely be a problem where you'll have to know the statement of the Silo theorem. Yeah?
Can we quote any results we get up to do in class or on the homework without proof?
Except in the case where at the last section where we'd say, prove that a finite integral domain is a field, you can't say in the homework we prove that the finite integral domain is a field. That would be it. But in the part of true false, absolutely. The key thing is to understand what makes this statement true or false. And that you can quote the material like the Silo theorems or things that we did in homework or things like that. Okay? Yeah.
How about proofs of theorems?
Again, it would have to be a fairly central theorem for us to ask the proof. And we're not going to ask the proof of a theorem that takes an entire lecture to do. Okay? I don't want you to memorize the proof of the Silo theorems. It's nice to know how the Silo theorems come about by a group acting on sets. It's nice to know how we classified groups of order PQ and of order P squared, without going through the entire rigmarole. Okay? But yeah, the Silo theorems are quite involved, and it would be ridiculous to memorize. I once had a math class where it just consisted of It was Math 212 when I was an undergraduate, and the exam was always the same. State and prove the closed graph theorem. State and prove this theorem. State and prove that theorem. So it just consisted of sitting there for hours and hours memorizing these proofs, which were incredibly involved. And then, 2 days later, fortunately, you remembered nothing about the closed graph theorem and things like that. So, I mean, my objective here is so that you become conversant with the language, and so that if you had to go to the book, you could remind yourself that the CELO theorem was proved by having groups of order P act on sets and figuring out what the stabilizer was and things of that nature. Okay? So let's go through the basic topics. So I'm going to do groups and vector spaces. So as I say, they're really these 3 units that we did. Groups, vector spaces, and fields. And commutative rings. Peter will do this review on Friday. I'll try to do the first part. Now, people should just ask me questions. I'm going to go down the abstract algebra study sheet. So the definition of a group, if we don't have the definition of a group, we're not going to be able to do much. So you should know that it's a set with a multiplication, an identity, an inverse, associative law. And you should have some examples of groups. And the examples of groups that we used all the time were the GLN over say over the reals, the multiplicative group of matrices that we got out of linear algebra, and the symmetry groups of a set. So all one-to-one maps of the set to itself. And you should understand why those are groups. And then, so that was the definition of a group. And then we had the definition of a subgroup of a group, which was just a subset stable under the multiplication, containing the identity, containing the inverses of elements. And we had the notion of homomorphisms between groups and isomorphisms between groups. And we identified that the kernel of a homomorphism was a subgroup of G, and the image of a homomorphism was a subgroup of G prime. And that the kernel was a special subgroup of G. It was a normal subgroup of G. And that was the definition of a normal subgroup. And then after this definition of normal subgroup, we showed that any normal subgroup could be defined as the kernel of a homomorphism. That's an important fact. Any normal H in G is the kernel of a homomorphism F. And the homomorphism map G to the coset space. And so you should recall, and this is an important abstract concept, first of all, how one defines this as a set for any H by making an equivalence relation on G of the different cosets. And this is the set of the equivalence classes, or the different cosets. And then it's a group under the multiplication GH times G prime H equals GG prime H when H is normal in G. And then this homomorphism takes an element G to the coset of G with respect to H. And because of this multiplication law in a normal subgroup, that is a group homomorphism whose kernel is precisely H, and whose image is all of G mod H. So this is onto. And then we had an important counting theorem that if G is finite, the order of G is the order of this subgroup H times the index of the number of cosets. And that can be viewed as counting the number of elements here by recognizing that each one of the cosets contains exactly H elements. So that was a useful counting proposition. So one of the most famous examples of quotient groups, so we made a special study of it, was when the group G was Z. We showed the only subgroups H were of the form n times Z, for n an integer, and that the quotient group was Z mod nz. Now, this has more structure than just a group. This actually has the structure of a ring, but in the group theory section, it didn't make any difference. this was a cyclic generated by the class of 1 mod n. And we made a lot of study of this group and arithmetic of this group because it's just a basic group, just as these are somehow basic non-abelian groups. These are very basic abelian groups. This is a cyclic group of infinite order, and these are cyclic group of any finite order. And we showed that an arbitrary cyclic group of order n was isomorphic to this group. Is isomorphic to Z mod nz. And the isomorphism, if I wanted to make the isomorphism, I would choose a generator. A cyclic group means one that consists of all powers of a given element. So choose a generator G, and you map 1 mod n in the homomorphism to G, and you map A mod n to the element G to the 8th power. And that's a surjective map because everything in G is of the form G to the A, and it only depends on what A is mod n because G to the n is the identity element. So, this is the basic. There's only one cyclic group of order n for every n up to isomorphism. And in particular, this. So then we took a little tour away from groups, but I'm going to stay. We went to vector spaces and fields, but from the point of view of review, I'm just going to stay inside the world of groups for the moment, and we'll come back to bases and things of that nature later. So. We then went on to study other interesting groups as groups acting on sets. So we made a big deal about group G acting on a set S. So this is just a homomorphism from G into the symmetry group of S. Abstractly, or another way of saying it is for every G in G and every element S in S, we have an element G of S in S. And G prime of S is equal to G of G prime of S. And that says that this is a homomorphism because multiplication in the symmetry group of S is just composition of maps. And when we had a group acting on a set, we had various concepts that we defined. We defined the stabilizer of an element. We defined the orbit of S, which was a subset of S. This stabilizer was a subgroup of G. And the orbit we identified with the quotient space G mod GS by mapping a coset GGS to the element in the orbit, which was G of S, some element S prime in the same orbit. And that only depends on the coset because this subgroup fixes the element S. And if we had a finite group, G, if we had a group acting on a finite set S, then we could decompose S as the disjoint union of the orbits for G. And therefore, the order of S was the sum of the orders of the different orbit spaces. And each orbit space was a coset space. So this was the sum of the indices of the stabilizers over the different orbits. And this gave us a very useful counting formula in a lot of different situations, depending on what action we took. So some examples of group acting on sets. So I would really divide the group theory, when I was thinking about it from a review to put it inside of my head. There's really three completely different sections. There's the abstract group theory, the definitions of the objects and the homomorphisms and the cosets. That's just completely abstract. That could be done with a set of symbols. Okay. Then there's the theory of the way groups arise, acting on sets as subgroups of the symmetry group of a set. So this is a very important realization of groups, groups acting on sets. And then there are tons and tons and tons of examples, like the symmetry group of S, or the linear group of matrices, or the cyclic group of infinite order, or the cyclic group of finite order. And you have to know these examples, and some of them come up from number theory, some of them, like the integers, some of them come up from group actions. So an example of And another example we used was the orthogonal group. On of R, which was a subgroup of GLN of R. And that was the things that preserved an inner product on Rn. Or if you put them inside of matrices, they were the things that if you multiplied A times A transpose, you got the identity matrix. And we saw that implied that the determinant of an orthogonal matrix was plus or minus 1. So we had that group. And then we did the group of motions. And that was the combination of the orthogonal group. Now that acts on Rn. It preserves the linear structure and it preserves the inner product. So in particular, it preserves the origin of the vector space. And the group of motions is something that's going to take any point to any other point. And that we call G or something. And that was consisted of all the translations together with On. So things of the form G of a vector was an orthogonal transformation of the vector plus another vector, B. So this was in On, and this was in Rn. And we saw the translations formed a normal subgroup, and the quotient group was the orthogonal group. So we analyzed the group of motions in a lot of cases and took a look at it acting on the set. This acts on the set Rn, or it acts on the set of lines in Rn. It acts on a lot of different sets that we can imagine. And we also identified finite subgroups of it and discrete subgroups of it. So we found, so this is all in the area of examples like this, the specific examples of groups. So we identified, let me erase a little here. So we restricted a lot because it was somehow related to Euclidean geometry in dimension 2. We did finite subgroups of O2. We showed they were either cyclic groups or dihedral groups. And then we did discrete subgroups of the motion group. And they had the form that you got a discrete subgroup L in R2, which was either 0 or multiples of one vector or multiples of two independent vectors. This thing was called a lattice. We proved that those were the only possibles for a discrete subgroup of the translations. And then you got a little finite group in O2. Well, at least a finite quotient group. And those we identified as either cyclic or dihedral. And we didn't put together all the possibilities, but we saw that only certain lattices admitted a larger group here than the group of order 2. So that was the that was the discrete group of motions. Now,
Excuse me?
sure.
I don't want to slow us down.
Not at all, not at all.
Point or something.
Yeah, yeah.
But when you, on the gamma there, I have to admit I'm a little fuzzy. And if it's not worthwhile for the exam, just...
No, it's important. So we discussed the finite subgroups gamma of O2. And it's not really gamma here. Namely, there's a group here, which is the discrete subgroup. Let me say it more precisely. So if we have a discrete subgroup here, let's call it...
I'm sorry, is that what you called the point group?
That's, yeah, there was the... If I have a discrete subgroup here, let's call it gamma discrete, then this L is the intersection of gamma with the translations, which is either this, it's either 0, it has no translations in it, it has translations by all multiples of one vector, or it has translations by independent vectors. And we discovered that if we took gamma bar, which was gamma modulo L, that was a finite subgroup in O2, which was G modulo R2. So that was the composition of a discrete subgroup of the motion group. First, you got a discrete subgroup of translations. And then if you mod it out, if you took that as the normal subgroup, it was a finite index, and the quotient group was a finite subgroup of O2, which we had already classified. And this was very restricted. That's what we showed. You couldn't get an arbitrary. So for example, in the case where L was a lattice, the order of this subgroup was at most 12, we showed. So it couldn't be an arbitrary cyclic or dihedral group because it has to preserve as preserves the lattice L in R2. Namely, when it operates on the plane as an element in O2, it has to stabilize the lattice. And that put a very serious restriction on which cyclic and dihedral groups we could have. Okay, so this is just a review to identify. Now, I'm not going to ask you to prove any of this on the exam, but I may ask you to recall the structure of finite subgroups here or the structure of discrete subgroups here. I mean, it'd be much too difficult to classify the discrete subgroups. Okay? Good. Okay, then we studied the applications of this formula in various group actions. And the most important group action is the group action on itself. G acts on G by conjugation. So if you have an element G, G of S is GS G inverse. So that's an action of a group on its own set by conjugation. That satisfies these axioms. And the orbit of an element S is called the conjugacy class of S. So that consists of all elements of the form GS G inverse for G and G. And the stabilizer of S is called the centralizer of S. So because this group action itself is so important, its orbits and stabilizers have their own names. And then we use this action to classify certain groups. For example, we proved that a group of order p squared was abelian, and that a group of order p to the n, if the order of G is p to the n, then G has a non-trivial center. And the way we did that was we wrote the order of G as the sum of the order of the orbits. So p to the n is the sum of the order of the orbits of S. Now, the elements in the center are the ones where the centralizer is the full group and the orbit has one element. So this becomes the number of elements in the center where OS has one element, plus the sum over G mod GS, where this is non-trivial. Namely, in this sum over here, where you have the index of the stabilizer, either the stabilizer is the full group and this number is 1, or it's not 1. Now, if it's not 1 and the group has order p to the n, this number must be of the form p to the k for k greater than or equal to 1. In particular, this term here is divisible by p. This term is divisible by p. And so this term has to be divisible by p. And this term isn't 0 because you have at least one thing in the center, which is the identity element. So you have to have more things in the center. So that was a typical example of how we used this kind of counting argument for groups acting on sets for this very important conjugacy action. And that would be a good thing to review. It's possible. Now, don't look at the. I mean, in previous years, people do slightly different things, but and then we use the notion of group actions to prove the CeLo theorems. So we have really only a few more things in groups. We had the CeLo theorems, where you had a group where the order was a power of p times a number which was prime to p. The GCD of that pair is 1. And the theorem said there exists a subgroup H of order p to the n. All such are conjugate and the number of CeLO P's divides M and is congruent to 1 mod P. So that's an important theorem, and you should look at the proof. I wouldn't memorize it. And then we use that to classify groups of order PQ. And we'll be using arguments like that undoubtedly on the exam. And then we had the final section on groups where we took a closer look at what conjugacy was in the symmetric group, Sn, which is the symmetric group on the set 1, 2, 3, up to permutations of n objects. And we showed that any element in G had a cycle decomposition where the lengths of the cycles summed up to n. You know, if this had length A1 and this had length A2 as a cycle, A3, A1 plus AK is equal to n, so it was a partition of n, and that the cycle decomposition determined the conjugacy class. So two elements with the same cycle decomposition were conjugate. And we showed how to conjugate one into the other. So the different conjugacy classes in the symmetric group are determined by the cycle decomposition, and you can work out the order of an element and all kinds of things if you know the cycle decomposition, right? So that, for example, if I had an element in the symmetric group on 7 letters, and it looked like this, and I wanted to know what the order of that element was, you'd tell me right away it had order 10, because I'd have to raise this element to the 5th power to be trivial, and this element I'd have to square it. And the element commutes with itself. So computations in the symmetric group become quite nice if one has this cycle decomposition. And I should say we did one other thing with groups, namely we identified various simple groups. So those are ones with no non-trivial normal subgroups. So we made a big effort to show that the group A5, which is a normal subgroup of the symmetric group, is simple of order 60. And we made a big analysis of it using the icosahedron. And then Peter went on to show you that, I think Peter showed you that, did you show them that? AN, which is a normal subgroup of index 2 in the symmetric group, is simple for n bigger than or equal to 5. So these are good family of simple groups. And that's another subject which we just introduced but didn't go that far into. Peter, is there material on groups that I haven't covered that would be important to stress here? So as I say, there are these, as I say, if I tried to organize my study, and that's what's really useful about preparing for an exam like this. It's not that you're going to learn anything new, it's that you're going to be able to organize material for your own thinking about it in the future. I would say there's the abstract theory of groups. There's the realization of groups. Acting on sets or vector spaces. And then there are the examples. And these things all feed on each other because the abstract CeLO theory lets us classify examples, for example, groups of order 15, et cetera. So there's a lot of interaction, but I would piece it together that way. No, 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 absolutely not. No.
But conversely, you should go through your notes because there may be one or two ways of thinking about things that are posed in class.
That's hard to believe. And there may be things in Artin that were better done in class. But you wouldn't have to repeat the argument in Artin if we gave a different argument in class, if that's the question. All right, while I have this up, let's talk a little bit about vector spaces, because that was the interim chapter that we really did before we could talk about the group of motions, before we could talk about inner products or or really what this group GLNR was, we had to redo the theory of vector spaces. So that'll be tested lightly, I think, on the exam, because I want to get to some of the ring theory, and the vector spaces I think many of you had before. So we started off with real vector spaces, by which we just meant Rn. And then we thought about them abstractly. Abstract vector spaces were just a set V, which was a group under addition with the identity element, the origin, an inverse element minus a vector. And it had one extra piece of structure, namely there was an abstract field, which we later found was a specific type of commutative ring. It's a commutative ring where every element has an inverse. All A not equal to 0 have a multiplicative inverse. And we had many examples of fields, like the real numbers and the rational numbers. And the field of P elements, we showed that this, where P is a prime, this ring is actually a field. And you talk about an abstract vector space, you have to have a field specified before you can give a vector space. So it's a group under the addition with identity element 0 and inverse element minus v. And then you have a scalar multiplication by elements A in F. Namely, you can take v to AV, and that has a distributes with respect to the addition in various ways. And then we showed that if you that this was an abstract vector space where you just took n tuples of real numbers, you added them as n tuples, and the scalar multiplication here, A times a vector v1 through vn, was just what you got by taking the multiple of each. And more generally, another example of an abstract vector space is just n tuples of elements in your field. That was the generalization of real vector spaces. And then we did a bit of a computation in the theory of bases and linear independence and spanning to show if V has a finite spanning set, over F. Namely, we can find a collection of vectors v1 through vn such that any v has the form summation of ai vi is some linear combination of those. If it has a finite spanning set, then v is isomorphic to m tuples over f for some m less than or equal to n, the number of elements in the spanning set. And this m was determined by throwing out elements in the spanning set until they became linearly independent in a basis. So we had the two notions of span and linear independence. And we showed that the number of elements required to span this space was greater than or equal to m, and the number of elements which could be linearly independent in the space was less than or equal to m. And if you had a set that both spanned and was linearly independent, that was called a basis. All bases had the same number of elements. And if you wrote an element out v in terms of a basis, that was a unique expression. And the coordinates of that element gave you the elements in Fn. So this is a really important notion to review, that this construction gave us basically all finite dimensional vector spaces. But to prove that, you have to prove that every finite dimensional vector space has a basis. So review the definitions of span, linear independence, basis. Know that bases have the same number of elements. I won't ask you to review all the linear algebra to prove this. But you should know at least that a spanning set has more elements than a basis. You should be able to identify linearly independent sets. You have to. Yeah, exactly. So that being the case, once we identified what all the finite dimensional vector spaces were, then it was natural to consider what were the homomorphisms and the isomorphisms between vector spaces. So we defined a homomorphism between vector spaces. Homomorphism was called a linear transformation. So it should be a homomorphism of additive groups that commutes with scalar multiplication. And we showed that if you took the kernel of T, it was a subspace of V, and the image of T was a subspace of W, where subspace is defined like subgroup. And we showed that if V is finite dimensional, the dimension of V was the dimension of the kernel plus the dimension of the image. And that was like our formula for the order of a group is the order of the normal subgroup times the order of the quotient group. So that was an important dimension formula, which is used all the time. And then we made a special consideration. We showed, by the way, that once if these were finite dimensional spaces, and if we chose a basis V1 through Vn of V, and a basis W1 through Wm of W, then we could represent T by an, I don't know, m by n matrix, where the mnemonic is that if you want to know what this column vector is, and I guess that's the kth column vector, you apply T to Vk, the kth vector of the basis here. And that's a vector in W, and then you write it out in terms of the basis W1 through Wm, and you get A, 1k, A, mk, right, where T of Vk is A1k W1 plus A2k W2 plus AMK Wm. And this gives a, then once you have the matrix, you have to know how it gives a linear operator back, and that identifies the linear operators from V to W, if they're both finite dimensional, with the m by m matrices under addition. And then we made a more detailed study of when we had maps from a vector space to itself, because then we get a ring, can be composed. And you get a ring, the endomorphism ring of V, usually a non-commutative ring of n by n matrices, because then you can multiply matrices. And in particular, the invertible matrices give the isomorphisms. Invertible, and we saw that a matrix was invertible if its determinant was non-zero. And that's a good thing to remember. Although we're not going to ask huge number of questions about calculating determinants. Invertible A, that's when P is an isomorphism. And the isomorphisms from V to V form a group, and that's the group we call GL of V. That generalizes GLN. And if V is finite dimensional over a vector space, this is the group GLN over F. N by n matrices over the field, which are invertible. Namely, their determinant is non-zero in that field. And we made a number of computations with this group. And we showed that you could study a transformation from V to V one at a time, not the whole group itself, but just one transformation by studying its characteristic polynomial. And its characteristic polynomial was the determinant of x times the identity minus t, which is a polynomial of degree n if v has dimension n, x to the n minus the trace of t, x to the n minus 1 plus. And we show that the roots of this polynomial were the eigenvalues of t. Now, all of this may have been a review for some of you, but it's an important review. We have to have that kind of linear algebra if we're going to go on and do detailed analysis of orthogonal transformations, etc. So I'll expect you to know this much of the linear algebra. Yeah, Tom?
On the third part of the exam, would you ask us to do computation and proofs?
Never really understood completely distinctions between computations and proofs, but no, it'll be more abstract reasoning, I think. But it's good. I mean, I might ask you to compute. I wouldn't hesitate to ask you to compute the characteristic polynomial of a 2 by 2 matrix or something like that. You should be able to do that. Okay? So, but sometimes people put down an abstract mathematician by saying, oh, he just does computations. But how can you do a proof without computation? I mean, it's all computation somehow. But so Peter will review a little bit more the theory of polynomials and their roots, et cetera, et cetera. But this plugs into the theory of polynomials. This is a polynomial in the ring f of x, and it's a very useful invariant of the transformation that can be used to study it. It doesn't quite determine the conjugacy class, but we did show that I should have said that. If you chose different bases to represent this T, then you'd get a new matrix T prime, which had the form AT B, where these were invertible matrices that did the change of basis. Actually, ATB inverse, that did the change of basis from the basis V to V prime on V and W to W prime on W. And in particular, if you chose a matrix for T with respect to some basis on V and you change basis, you'd get a new matrix. Sorry, this is all wrong. Let's try this again. We represent the transformation by a matrix A. If we change basis, we get a matrix BA, B prime inverse A prime, a different matrix, but it would have this shape. And in particular, if we change basis on V, we'd get a matrix A prime that looked like BA, B inverse. And it turns out that the characteristic polynomial depends only on the transformation. So the characteristic polynomial of this matrix would be the same as the characteristic polynomial of that matrix. And you can prove that to yourself by the fact that the determinant of BA is the same as the determinant of AB. Even though the matrices don't commute, the determinant commutes, because both of these things are equal to the determinant of A times the determinant of B. And once you get down to the field, things commute with each other. So this seems like a lot to remember, but I think if you package the theory of vector spaces very much in the language of the theory of groups, these are like homomorphisms, these are the properties like homomorphisms. The one thing that's really new to vector spaces is that unlike the theory of groups, where we don't have a natural way to represent every group, we know how to represent a cyclic group and things of that nature. But once the groups get more complicated, we don't know what they all are. In the case of vector spaces, we know what they all are. And this representation of a vector space lets us somehow pick apart the theory of the maps between vector spaces. So since we don't even know what all the groups are, it's hopeless to classify the homomorphisms between the groups. But in vector space, we can classify the vector space using a basis. Then using the basis, we get a nice model of the linear transformation. And then we can investigate the transformation a little bit more closely and its eigenvalues using the characteristic polynomial.
Next to the characteristic polynomial, you write little f of x and then big F of x.
Yeah, the polynomial is this determinant. That's this polynomial of degree n. It's an element of the ring polynomials in one variable over the field. That's all I meant. I mean, we hadn't studied this ring at the time we discussed characteristic polynomials, but what we're doing is making an invariant that starts with a linear transformation of a vector space over a field and produces an element in this ring. And then the theory of this ring, like factorization and roots and things like that, gives us information back about the vector space. Right? So there's a lot of interaction, if you step back a little bit from the course, between the groups, the rings, and the vector spaces. And that'll be a fun thing in the course of the review to see. Okay? Questions? Is it all clear? Or you're just beginning to do the study? Okay. Well, as I say, I'm going to be around. Don't hesitate to send me email. Don't hesitate to bother Peter. Peter, yeah. Cookies, absolutely. Not just cookies, we'll have cakes and everything. So all right, I'll bring some good stuff. It's in Boylston, right? Next Friday afternoon. The way our wonderful calendar is currently organized, I think the distance between the last lecture and the exam is what, 6 weeks? So think about that when the subject of calendar reorganization comes up in the curricular review. How much nicer if we had all taken this exam earlier. On the other hand, let's take advantage of this schedule as it's currently organized to put this all clearly in your head, and then you'll be in a good situation to go on with 123. Good. Okay. See you later.